Okay. So, yeah, we talked about the notations and everything. Let's quickly get... Yeah, so let's start with a very brief breath awareness. You want to do it? Get your attention on your breath. Yeah, this is a paper I found. Mindful breath awareness facilitates efficiency gains in the brain network. So anyway, there's some study, not a very old study, 2018 study, and that's what it is saying. So yeah, it helps you to get really focused. It helps you improve your attention very, very tremendously. But anyway, so I'd request everybody to be on time. We have, the class starts at 11 sharp, and the previous class is supposed to end at 10:50. I'll try to finish well in time, but we have to start, and for that we have to start on time. So I see many students even coming back 10 past 11. So try to come early. Maybe what we'll do is in the first 3 minutes take attendance. And when we take attendance, make sure that your phone is connected to the institute network. Don't use your Wi-Fi for this. We'll figure that out, but yeah. Anyway, so today is going to be a little bit of historical lecture. We talk about shallow neural networks, and you've already done neural networks in your machine learning course. We'll just do a very quick recap, but we'll go over the ups and downs in the machine learning that have happened, and what are the key milestones in machine learning. So this was what we call a shallow network, or the conventional neural network. And what we have is an input layer where the input feature vector is given to the network, and we see how we convert the input into a feature vector, which is in the vector of numbers. And here you see the ith example, which is a feature vector in m-dimensional space. M could be very large. For the imaging problem, it could be as big as 3 million, if it's a 1000 cross 1000 RGB image. And then there is a hidden layer, and we are going to represent the weights as W superscript 1. So superscript means which layer it is, and subscript means the corresponding weight matrix. So in this particular case, the first layer has, let's say, U units. So we have W subscript 1, W subscript 2, all the way till W subscript U. Remember, we talk about logistic, we only had one weight vector. Each of those WUs or WJs are essentially m-dimensional weight vectors. So here what happens? You multiply this input with this weight vector W superscript 1 subscript 1, which is m-dimensional vector, and you get the input to this hidden layer. We'll denote it with Zi. Right? So the input would be, so this will give you Z, again superscript 1 and I, corresponding to the ith example. And that's a scalar. And then we apply the activation function, just as a logistic regression is sigmoid, and we get A1I in the output. Right? When we apply the sigmoid function. Now the second unit, we get Z superscript 1 subscript 2, which is again a scalar. And again we apply the activation function, we get A1, so this is A1 1I, A1 2I, okay? And this would become A1 UI, corresponding to the uth hidden unit, right? So that's the output. And then you do the same thing again with the weight vectors W2, W superscript 2. Now in this case, this weight vector, there are k units, so we are thinking of a k-class classification problem. So I get k outputs, and we can apply the cross entropy loss as in the case of multi-class logistic, and we get the final output. Yes?
That Z1I, if I is fixed, then how can you get Z1 to
Z1 to I, and this is Z1 1I. So, yeah. Yeah, so for each example, we get a vector. So Z1 is a vector in RU. u-dimensional space. Right? We have u units. And again we apply W, we get the outputs. Yeah. I is the example. I is the ith example. Ith example is a feature vector. You give that example as the input. So these are xi1s to xims. You get the output which is z1i or this layer, and then when you apply the activation function I get a1i, and then the next layer will get z2i, and then this will give you a2i for that example, and this will give you the probability vector, and then you apply the cross entropy loss function, you get the final loss value. Right? Now we view generally loss as a function of the weights and the biases, which are the parameters of the neural network that we have to learn. So typically this is summation over loss of W comma B and examples xi. I is going from 1 to n. Right? So I take the loss, sum it over all the examples, and that's my total loss. And now the objective of my neural network is to find the parameters W and B which minimize the loss, which are the optimal parameter in some sense. And last time we looked at, for logistic, we looked at 3 different loss functions. For neural networks, all those discussions apply, but there's something more also that comes in. Right? How do you actually learn those parameters? And this has been a very important and, interesting issue. So this is the same thing in a little more detail. So, so same thing. So what I do is, here there's input, I weight by the corresponding weight vectors, and I sum it up, I apply a bias term, I get Z11. Again, I is implicit here, but I can also subscript I here, and then when I apply the activation function, I get A11, and similarly A12, and so on, and apply second layer weights, I get the second layer inputs and outputs. Okay. So my model parameters in this case are W1, B1, W2, B2, W superscript 1, B superscript 1 corresponding to the first layer, W2, B2 corresponding to the second layer. Now this W is now a vector. So if I look at W superscript 1, it's a vector which is M cross U. Because for each input, there are M dimensional feature vector, and then I'm giving a U dimensional feature vector as the output. So this can be thought of as a M cross U vector, and the biases can be thought of as a U dimensional vector. Similarly, the second layer weights are U cross K vectors. To go back here, you look at the weights here, the input here, so this you can think of as the input to the second layer. And this input has size U and the output has size K. So the weights W2 is U cross K. And the biases at the second level are K dimensional. Okay? And so on. You can think of a deep network also, but let's start with a shallow network. So, the neural network have a very long history. So, for example, the first paper on the neural network was in 1943. It was by Warren McCoy and Walter Pitts. I was looking at the historical data. Here are those people. And this is the paper. I just was able to get access to the paper. A logical calculus of the ideas immanent in nervous activity. So, this is about the time when we figured out the structure of the nervous system, microscopes were designed, and we could actually see neurons within the network. And, what they tried to do, if you read the paper, they're trying to explain how the brain works, the neuron works. So this paper actually built a mathematical model for the working of the neurons in the nervous system, in the brain, in the human brain or in the animal brain. And in this paper he says, here is the mathematical models, and these neurons are connected to each other in the complex networks, and this is how the brain does the computation. 1943. Okay. This is again, see, different types of neurons and connectivity which I took from that paper. And these are hand-drawn. We didn't have computers and printers at that time, so these drawings are all hand-drawn. Interesting. Okay. Then the real neural network actually came in 1958 when this Frank Rosenblatt's paper on perceptron. And this is a paper, a probabilistic model for information storage and organization. And he actually showed that given this perceptron architecture, which is very similar to the logistic regression of a single neuron in the neural network, how you learn from them. And he was able to learn if any set of data points are linearly separable, you should be able to. He showed that you can actually learn the correct decision boundaries. So this is in the true sense the first, perceptron or first neuron kind of a paper. And the idea is very simple. So again, a neuron has the inputs, a perceptron is an output. Output is Y, input is X, and then you do W transpose X plus B. And unlike a sigmoid function, he suggested in applying a binary function. So you just threshold it. If W transpose X plus B is greater than 0, then you output a 1. Otherwise, you output a 0. And so it was a step function instead of a continuous, smooth, sigmoid function. And what is the learning rule? Very simple learning rule. So W is W plus, so T is the target, okay, and Y is the output of the network or output of the perceptron, okay, and this is the learning rate. Okay. So you think about this algorithm. What is he doing? Looking at these weights. Let's say target is 1 and Y equal to 0. Okay. Of course, you do it for all the examples. But let's say for a given example, target is 1, Y is 0. So this term would be positive. Okay. Now X is of the same size as the weight vector. Okay. So, and eta is positive. So what are you going to do? Which weights are you going to increase with this update rule?
Positive X.
All the positive xi is that weight, and the negatives you are going to decrease. So once you do the update, what do you expect for the output to be? It is going to become more, because the positive weights have increased, negative weights have come down. So therefore, the next iteration, the output of Y will get closer to T. And since you are averaging it across all the inputs, so it's going to just try to do that. And similarly, if this thing is the opposite, if T is 0, Y is 1, you can apply the same logic and show that it actually tries to get there. And they proved that if your data is linearly separable, then this algorithm will actually learn a correct decision boundary. So I'll leave that as your homework, which is not graded. Just try to work out the proof. If two classes are linearly separable, what does it mean? That there are these crosses and zeros, and there is a separating hyperplane which separates them. And try to say that this algorithm with a suitable learning rate will converge and find the correct decision boundary. Okay? This is what they proved. And then at that stage there was a lot of excitement that we have figured out how the nervous system is. There's these neurons that are interconnected, and I've also figured out a learning algorithm. And that led to a lot of interest in artificial intelligence, that now we can simulate the brain and all of that thing happens. So this was the first AI sort of excitement, or machine learning, or neural network excitement. But then came this book written by Minsky and Papert, and it actually punctured all the enthusiasm. And what did this book say? He actually looked at this perceptron and analyzed it in great detail. But to tell you the long story short, he said that perceptrons are highly limited. There are lots of limitations. And he's looking at single layer perceptrons. So the input, perceptron, output. Right? And he says that these perceptrons cannot even learn the XOR function. So if there are two inputs which are binary, and your output is supposed to be XOR of that, he showed that, a single layer perceptron cannot learn XOR or a parity function. So all that excitement just melted away, saying, neural network can't learn any complex functions. And this led to the first bust in the AI. Funding agencies stopped funding AI projects, and we call it the first AI winters. 1969 is when they wrote this book. 1970s, people stopped working in AI network. All that enthusiasm went away. Okay. But again, 1986, the interest restarted again. And that happened because of this seminal paper by Hinton. Hinton is considered to be the father of AI. And it's remarkable the kind of breakthroughs that he has done. So this is really the paper that actually shows that how to learn a perceptron. So he actually looked at the shallow network that we were talking about. He made that network and he gave a backpropagation algorithm. And this is what we use even today, how to learn such a network. So he made this architecture. He said, okay, if you have an architecture like this, you have a loss function, and then you differentiate the loss function and then backpropagate that, use that to update the weights, and this is how you learn a network. And he showed that XOR and the parity problems can be solved because it's no longer a single layer perceptron, it is a hidden layer as well. So from the input you're not directly going to output, but through a hidden layer you're going to the output. So this I've just directly taken from his paper. So we have run the XOR problem many times, and with a couple of exceptions discussed below, the system has always solved the problem. Figure 3 shows one of the solutions to this problem. The solution was reached after 558 iterations and 4 stimulus pattern leading to a learning rate of 0.5. And this is, I think you would have done, in classical machine learning course, that how to implement an XOR using the neural network or using this one. So he has given the weights. There are two input units, one hidden unit, and then one output unit, and he has given the weights and how to do the XOR network. And then he talks about parity also in this paper, because these are the two things that actually gated, that stopped the AI progress in that sense. And he is saying that he's referring to the Minsky book. It's a parity problem. And what he says is this is a very difficult problem. And XOR is a special case of parity with size of 2. And so in this architecture, it requires at least n hidden units to solve the parity patterns of length n. So if I have to find the parity of n bits, then you need to have n hidden layers, and he showed that, with this network, you can actually solve it. So this was 1986, and about 3 years later, there were a bunch of papers that are talking about how neural networks could actually approximate a lot of functions. So this is a classical paper by Sibenko, and he says that the neural networks are universal approximators. So you can think of a neural network, you are giving some input, you are expecting an output. Let's say it's a real valued output you are expecting. So you can think of neural network as learning a function. And what they showed was that with this architecture, you can learn any function. That's what we mean by universal function approximation. With sufficient number of neurons in the hidden layer, the neural networks could learn any functions to arbitrary degree of accuracy. So if you need more accuracy, you have to put in more neurons in the hidden layer, but you will be able to learn that function. And there's a bunch of papers with different assumptions, different types of activation functions. They showed that you can approximate any other function. So I've listed down here 3 such papers, slightly different assumptions, and they all show that neural networks actually act as a universal approximators. And this led to a renaissance in neural networks. XOR is no longer a problem, parity you can solve, and now the neural network can approximate any function. A lot of interest, funding agencies started funding that time these networks. And there was supercomputers were being connection machines, so to highly interconnected networks to simulate neural networks, because we didn't have very high speed computers at that time. So it required parallel processing. So those kinds of systems were getting built. And at the same time, we had the invention of what are called the CNNs, convolution neural network. And this is a very interesting paper that showed that how the convolution neural network can be used for the digit recognition problem. So this is a very, digit recognition is a handwritten digit recognition problem, also called the MNIST. This is a classical benchmark of that time, that anybody who was building anything with neural networks or machine learning, they had to report the performance on the MNIST data set. And this was the benchmark at that time. And this was a time when support vector machines were hot, because they were outperforming every other model. And this paper, I just took this from this paper, and you can see here that this is VSVM poly 9. So I think a ninth order polynomial kernel with support vector machine, we are getting an error of 0.8%. So that was the best performing, state of the art at that time. And these people propose convolution neural networks, and there are different variants of their algorithms, and then they are getting a performance of 0.7. Significant improvement over that. And that sort of, led to a lot of interest in neural networks again. However, this interest was short-lived because of a very fundamental problem that I alluded to in the last class also about, the vanishing gradient problem. So, the papers were showing, there are many results that were showing that deeper networks you build, the more learning capacity it has. And when you build a deep network, then because of the vanishing gradient problem, it's very hard to learn those networks. And this actually led to a lot of issues. So many people designed networks, but they were not converging, they were getting stuck in a local minima, not getting good results, and many problems were happening at that time. So there was a lot of initial enthusiasm, but they could not really beat the neural network-based machine learning algorithm could not beat, the top of the line performance at that time, which were like support vector machines, maybe some boosting type of algorithms like ADA boost, random forest, and stuff like that. So they were not able to outperform those methods. And that led to the second winter. That interest died down. You would not get a tenure in the US university if you were working on neural networks, and all that thing happened. And hardware were very slow, the networks were, taking a long time. And there are these two fundamental breakthroughs that happened between 2006 and 2012. And again, both of them are by Hinton. And this man is remarkable, We see that, if an area becomes nobody is interested, then people change their area, they go to the next hot thing. But Hinton continued to work on the neural networks despite all those challenges. So first he showed that XOR can be circumvented. Then there was a lot of enthusiasm. Then again the enthusiasm died down. He continued to work on this. And he designed this architecture called the deep belief networks. And through this he showed how to train the deep networks. But there was some hope, but still it was not really it did not really make too much of a difference. The key turning point came in 2012, when again, this was again a paper by Hinton and colleagues, when, now MNIST was, much better solved, but its place was taken by another problem called the ImageNet classification problem. Bunch of images, lots of classes, you have to classify which category the image belongs to, okay? So, this is the title of the paper, ImageNet Classification with Deep Convolution Networks. And this AlexNet architecture, they achieved a performance of 15%. And the previous best was 26%. So it's there was a competition, worldwide competition on this ImageNet. And this is, typically algorithms improve by 1 or 2%, but 10% improvement was unheard of. So this is really led to a lot of improvements in AI and machine learning. And after that, a bunch of algorithms came in, VGG, Inception, ResNet, all of going bigger and bigger networks, deeper networks. So now deep learning, basically the difference between neural network and deep learning is that in the deep learning you have many more layers. So we talk about a shallow network, it has three, the input layer, the hidden layer, and the output layer. But in deep networks you can have hundreds of layers. And the basic problem that we have is the vanishing gradient problem that we'll discuss a little bit later, that you can't really train those networks. But with these innovations, the convolution neural networks and the Hinton's innovations, those problems were solved. And that led to a deeper and deeper networks, and they were able to solve these imaging problems to very high degree of accuracy. Okay? And then the next breakthrough came in with this paper by Google, which said attention is all you need. And that led to this, that's the foundation paper for the large language models. And then a series of papers, BERT transformation, GPT and all. And the rest, I guess you all know. So, yeah, that's sort of a brief up and down of the neural networks. And we are going to cover many of these papers in the class. Some of them you are going to read and present as well. Yeah. Any questions on this so far?
What is the next breakthrough?
Huh?
What will be the next breakthrough?
What will be the next breakthrough? That's hard to predict, I mean, right now, yeah, that's a very good question. In terms of the capacity, have you seen those videos of humanoid robots walking on the street? Right? So that we are able to do that, and most of the cases, the neural networks are able to surpass human performance. Right? So earlier we thought that chess is a place where computer cannot beat, but we have the deep mind which bet Kasparov. And then we thought a game like Jeopardy, where it's like a quizzing game, computers can't beat, but there also computers bet them. But then AlphaGo, we thought that is a more complicated game, but again, 2017, I think the computers bet, the best human champion in AlphaGo. Then we thought maybe computers cannot, do a language kind of a task, which is very vague and ambiguous. The large language models, they are also, now they are sort of, indistinguishable from human performance, at least in terms of the sentence formation and parsing and blah, blah, blah. And I was talking to somebody, there's some PR released by Google and OpenAI, and they are saying that their deep learning models are actually matching the gold performance in the International Maths Olympiad. Right? Huh? What? Gold medalist. So we thought that these deep learning cannot crack very deep mathematical problem, but even that is happening. They are actually not surpassing yet, but they are matching the human performance there. So everything that humans do can be done with AI now, right?
But it is taking a lot of power right now. It's
What?
not feasible in long run.
But you have to build that model once, no? Once you build a deep learning model, once you build a transformer model, then you can use it. People can just kind of, yeah, indeed, yes, it takes a lot of training time, a lot of power, a lot of GPUs. But it has to be done only once. Yeah, so that brings me to a very important aspect of AI, which I was not planning to talk, but I'll just briefly touch on. Maybe we'll talk about ethics of AI. So, if machines can do everything, then what will happen to the society? What are we supposed to do? And where are we going with that? Right? So we can build farming robots, right? Huge tractors that can do the farming, right? They can sow the seeds, they can cut the crop, they can separate the grains they can pluck the fruits and flowers and everything, pluck the fruits and whatever we need. Even they can make food for you. So they can construct your houses as well. They can construct clothes, right? So if all of this can be fully automated, then there are only two things that can happen, right? The power would be, either concentrated in a few hands, and they get all rich, all powerful, they try to exploit other people. But let's say the governments intervene, and they say, okay, I'm going to distribute the wealth equally amongst all the people. Then humans have nothing to do, right? You get free food, free everything. So what do you do then, Yeah.
Exploration.
Huh?
Exploration.
What? Exploration of what?
Of the world or outside space or something like that.
Yeah. Yeah.
So many humans, everyone will explore outside.
Everyone will explore outside. And what if this thing goes into wrong hands, right? What if happens, two countries, they start fighting with each other using AI? That's going to be a very scary scenario. So we have to think about these things. So this is actually as powerful as the discovery of an atom bomb, because it's already happening. No, the aeroplanes, the unmanned aerial vehicles, they can carry a nuclear payload in the fuel, and they can actually just give the coordinates. You don't even have to give the coordinates. You can just give the description that okay, in this city I'm going to look for, whatever. Give some brief attributes, and then anything. It's really open what's going to happen, right? So something to think about. Yeah.
Will there be third winter for it?
Now it has come to a stage where it is surpassing human performance. So I think now it cannot be the third winter in that sense, but there can be a third winter in some other sense.
I think it's
Huh?
like there would be a time like after 10, 15 years
Huh.
where nothing new could be like discovered in this field because
Okay. Why?
So because they need more and more, it is 10x to some power. That 10x training you will provide, then it will 10%
Improvement.
Yes, sir.
But that, I guess, some breakthroughs can come, right? Some algorithmic, for example, DeepSeek was an interesting breakthrough. It was an algorithmic breakthrough that led to, smaller models and better performance. So similar breakthroughs can still happen. But the way computers and the internet has shaped the society, I think that's the same way that deep learning will shape the society, AI will shape the society. Because a lot of the tasks, see, what happens is first wave, the technology demonstration, right? Second wave, it actually comes to the society. It gets adopted in the society. And how is it going to get adopted in the society? Right? I give you an assignment, you're going to use ChatGPT to do the assignment, right? Then I'm going to use ChatGPT to make an assignment. You go to a court case, right? The lawyers are going to use ChatGPT to give their argument. The judges are going to use ChatGPT to judge the cases, right? So, the society is going to do that. And autonomous vehicles, autonomous systems are going to be, more and more there in the society. Now, what the society does with that. So, for example, internet is ubiquitous now. All the transactions are happening there. Everything. Think of anything. You can't imagine in such a small device you can do so many things. Similar things may happen for the deep learning, and that will take another 10 to 15 years to actually percolate down the society. But what is the form it will take, we don't know. And it may just happen that if that power gets concentrated in a few hands and there is a lot of joblessness in the society, which is already signs are happening, right? World overall, economies are closing down because of this fear. And the society may reject AI, saying nothing to do with it. I don't want AI. If it cannot, it takes away my food, what will I do with this? So the society as a whole may just reject it, and that could, I think, lead to the third winter. Or maybe a major event like a world war or something. That could lead to an event like that. We don't know. So I want to quickly finish this thing I was thinking. So yeah, we'll have this discussion more later. But I think we should be mindful of this important issue. Because so far we are thinking technology is neutral. But it does have a lot of impact on the society. And yeah, so how does that impact? Yeah, we have to, I don't know how to sort of, knowing that the impact may be sort of detrimental, what do you do about it? That's the big question. And there are some people who are actually making noises about it, they are actually talking about it. But anyway, so let's come back to this. So function learning. So you have an input and we have an output. And let's look at just a 3-layer network. There's just one hidden layer with U units. And this function is a real number. And output Y is also a real number. And let's use, just for simplicity, sigmoid is a more difficult activation function. So let's use what is called a ReLU activation function. So this is the input, Z, and it is 0 when Z is negative, and Y equal to Z if it is positive. So instead of that, we will use the ReLU activation function. So now my question is, can you design a network that will approximate any function? So I need Y equal to f of x. I have been given this function. So this is x, and let's say I have been given an f of x like this. Any arbitrary function. And I want to approximate this function using this 3-layered neural network. Can you do that? Only one hidden layer. So how do we think about doing it? So maybe what I should do is, if this is x, this is f of x, and this is my function that I want to approximate, I can think of it, divide it into segments, right? And think of it as, piecewise kind of a linear or constant within that segment, right? So I can do a piecewise linear approximation to this for each of the segments, right? Okay? And if I can approximate within these segments, then I can make the segments come close to each other and then get to the arbitrary degree of approximation. Okay? So, what if I could implement a function like this? X, and this is y, a step function. Let's say this is my x naught, and let's say this is x naught plus delta x, and this is delta y. So with that neural network, if I could implement this function, then I can also implement a negative of this, a step up function as well as step down function. And I can choose my x naught and delta x and delta y's. Right? So if I have this, then can I approximate this function? Huh? Yes, no? No? Okay. Let's. Yeah. So what I can do is, for example here. So my first approximation could be a delta function which kind of goes like this. But then the next time step, it is slightly increasing. So then I can add another delta function that goes from here like this. Right? So now if I add these two, I'll get a closer approximation until this peak. Then I can add a function that goes something like this at this peak. Right? So then if I add these three functions, I'll get something like that goes up, up, and then down, and then flat. What is this? So please make sure your mobiles are not, notifications are switched off. Okay. And so on. So I can think of this whole function as a stepwise function that are doing steps, either positive or negative, in different time points. So how do I implement this function? How do I implement this function? So I have my x, and this is my ReLU. So I need to have, let's say, W1 and B1. And let's say W2, B2. Okay? So what does ReLU give me? This is my ReLU activation, right? It gives me like this. But I need it to go only after x naught. So I can set my, and then what is the slope I need? My slope would be delta y by delta x. So maybe I can set my W1 as delta y by delta x. Okay? So when x equal to x naught, what will be my output? So, okay, if I put this slope here, then what I will get is a function that goes like this, where this slope is delta y by delta x. But I need this point to be at x naught. How do I do that? I add a bias. So my b1 would be minus of x naught times delta y by delta x. So my b1 is minus delta y by delta x times x naught. Okay, so let's look at my first output. What is my output? A1. What will it do with these two weight functions? A1 is h of W1 x. I only have one input plus b. This is h of, what is W1? Delta y by delta x times x minus delta y by delta x times x naught. Okay? So this term is greater than 0 if x is greater than x naught, right? And less than 0 otherwise. So I can write this as, so my A1 yeah, what will it be?
Like in terms of
Delta y by delta x times h of x minus x naught, right? Or I can say x minus x naught plus, if x is greater than x naught, it will be that. So how will it behave? At x naught, it will be 0 and then it will go with the slope of delta y by delta x. But I needed a step function like this, right? So I can add another unit which behaves the opposite way. So this I want to behave, let's say, from here, let's say x naught plus delta, and it goes minus with the same slope, right? And this point will be x naught plus delta x. Right? And this weight I will give as, here I'll get w equal to 1 and here I'll give w equal to minus 1. No, here I have to give a positive slope because I want an increasing function here. So w2 would be same delta y by delta x. w2 is delta y by delta x. b2 is delta y by delta x times x naught plus delta x. Right? So this will be another step function which will be like this, right? And this point will be x naught plus delta x. So this is A2 and this is A1. But I subtract A2 from A1. So the next layer weight I make minus 1 for this one. So if I do this, I get a piecewise step function. So now if I combine this, so here at the next layer, if I just combine these two and I add these two, what do I get? I get my output, which is from 0. So this is x, this is y, and this is x naught, and then it's going like this. This is x naught plus delta x, and this is delta y. So just by using two hidden units in the ReLU activation function in a suitable way, I can make a step function like this. Now I can make multiple such step functions, and I can again put the right values at x naught, at delta x and delta y, and use that to approximate any function. Right, so this is one example where we show that we can approximate just by a 3-layer neural network any function. And the universal approximation theorem does it more rigorously with more general assumptions and many more things. So that's about this. How about classification problem? So right now we look at a regression problem. A 3-layer network with a ReLU can approximate any function. So I should be able to learn any function with that, right? How about classification? What kind of decision regions or what kind of decision boundaries I can create with, again, a 3-layer neural network, a shallow network. So I'm out of time. We'll discuss it in the next class. Think about it. That, we can't visualize in m dimension, but we can definitely visualize in 2 dimensions. So if there are 2 inputs, and we look at, in the case of logistic, we can think of it, the decision boundary being a line, or in general a hyperplane. But now with a neural network, which is a shallow network, what kind of decision regions can I create with that? And we'll see that, even with this it's quite powerful. We can create variety of decision functions, decision regions. And now when we go deep, then what is the power we get from the shallow network to a deep network? That is something to think about. Okay? So thank you all. We stop here.